Hi, my name is Jordan Thompson. I'm heading business development for Talyn Air. We are an eVTOL company building a two-aircraft eVTOL system, and I'm here at Oshkosh with the AFWERX team. Talyn's taking a fundamentally different approach to the eVTOL architecture. Both of our founders came from SpaceX. Evan, who's our CTO, worked very closely on the Crew Dragon, and Jamie, who's our CEO, worked very closely on the Falcon 9 reentry. And they were very familiar with the multi-stage rocketry approach. Each stage of a rocket needs to fulfill a different mission, and similarly that's true for eVTOL. You have the up and you have the out. So that vertical flight has a very different set of requirements compared to the forward flight. And taking that approach, you realize that people butt up against the same constraints. It's going to be relatively similar batteries. It's going to be the same laws of physics. And the only way to extend the payload and range capability of a fully electric system that is 100% battery electric and not relying on non-renewables is to actually separate those two stages, and that's exactly what we're doing here. Both of our aircraft can be seen over my shoulder here, and what you see is a rotor wing hybrid aircraft that's essentially a tugboat. And its job is to divorce you from any runway requirements. Its job is to lift a fixed wing aircraft to elevation, transition off the rotors onto winged flight, and then deploy that fixed wing aircraft to fulfill the forward flight mission. So our two aircraft system has a different mission profile. The concept of operations are going to be unique in that sense as well. Our lift aircraft is going to get the fixed wing aircraft to elevation, transition to forward flight where it's getting lift off the wings, and it will deploy the cruise aircraft, that fixed wing aircraft, the passenger aircraft, to fly forward to its destination. That lift aircraft will then be able to loiter, receive an incoming cruise vehicle, or it can land itself and wait for the next incoming cruise aircraft. At the destination, our cruise vehicle is going to be able to perform conventional landing, or it can have a mid-air docking with a similar lift aircraft, which will give it the vertical landing capability. The fixed-wing aircraft, that cruise aircraft, is essentially a passenger. It's a parasite aircraft in the vertical take and landing. The primary benefits that come from breaking out the two portions of the mission are the fact that you no longer have to carry the dead batteries that were expended during takeoff, and you don't have the drag of the rotorcraft. Further optimizations are also possible. There's a very different powertrain requirement for the vertical takeoff, and there's a very different powertrain requirement required for the forward flight. So you really get additional optimizations, but the primary benefits come from not having the drag from those rotors and not carrying dead batteries for the entire mission. So this aircraft system that we're building right now is built off of a 36-foot wingspan lift aircraft. It's going to have its own capability of working with a 100 to 500 pound payload capacity, and you will also be able to use that cruise aircraft to extend the mission. So you can fly a lot farther, and you can take about 100 to 150 pounds, about 100 miles. The capabilities are in line for a commercial pathfinder that fits nicely in cargo delivery, cargo logistics, and also medical logistics. Those are the two primary commercial sectors. In terms of what we're doing for the Air Force with an aircraft system of this size, is we're proving that it's scalable, and we're also offering a forward resupply capability that is fully autonomous. This is a fully scalable system. Future generations of this aircraft system are going to be designed to lift existing ISR platforms that the military is very familiar with and get those into the air. Essentially what we would be creating for the Air Force is a mobile landing strip, a mobile way to launch where you don't have the ability to take in a tarmac. It gives you the ability to have ad hoc forward operating bases that would otherwise be impossible depending on the theater. This is definitely a complicated technology. The hardware and software are not as straightforward as you would have if you operated these two systems in unison. In exchange for that, you get the freedom to give runway independent operations to different airframes, and you also get to stay 100% battery electric and extend the payload and range capabilities and maintain the simplicity of your overarching aircraft system on a system by system basis. And what that means is if you compare an internal combustion engine vehicle to an electric car, the decrease in moving parts allows you to have much better direct operating costs for whatever mission you're fulfilling. Something that's really exciting about what we're building here is the fact that we're doing it completely autonomously. There is definitely complexity in getting two aircraft to work together in unison. Obviously, everybody's familiar with mid-air refueling. There are a few lesser-known projects where they've actually been able to dock two piloted aircraft together. FICON is a famous example. What we're doing now is taking that and putting that all into our GNC and our autonomous systems so that these can be done repeatably without a human in the loop. So Talyn Air is located in Culver City. We're about 15 minutes from Los Angeles International Airport. To date, we've been testing in the desert with our subscale aircraft, and we're proving that the actual operations of two aircraft deploying and docking in midair is feasible. Simultaneously, we're working for Agility Prime, part of the AFWERX group, on the full-scale 36-foot wingspan aircraft that I've been discussing. That test program is going to be carried out at Edwards Air Force Base, and we're very grateful to have those facilities and resources available to us.